Hey, hello, welcome to Advanced Algebra 2. We are still working on exponential and logarithm functions. Here we have the last set of notes that are explicitly about these things. And today we're going to solve equations, both exponential equations and logarithm equations. And as you'll see, one will turn into the other, and the other will probably turn into the one, but not necessarily always. So, for example, in this first equation here, we've got some 64s to powers and 16 to powers, and it just works out better if you trade them both for powers of 4. So 64 is 4 cubed, and 16 is 4 squared, so it's 4 cubed to the x, and then instead of 16 it's 4 squared to the x plus 1. And that's helpful because then we can do the power of a power rule, so it's 4 to the 3x on the left side, and on the right side, it's the 2 times x plus 1. And that just means now that since they're equal and they have the same base, you can just make the exponents equal to each other. And then, we're just solving a little dinky equation at this point. So 3x equals 2x plus 2. If you subtract the 2 x's, you get x equals 2. And you're feeling hunky-dory and good for yourself. And you should. That's our first example. Now, the second one isn't quite so pleasant. It starts as 6 to the x equals 27, but there's nothing nice you can do exponent style like the first example. So you're stuck changing it into logarithm format. So as a clue, whenever you're looking at x and it's in the exponent and you don't want it there because you want to be able to do things with it, logarithm format. So that turns into log base 6 of 27. And then to go ahead and make an exact answer, you'd say x is log base 6 of 27, and that's true. If you're you're a common log kind of person, you might turn that into log of 27 divided by log of 6. That's also true. If you're a natural log kind of person, and you should want to be, it's natural log of 27 divided by natural log of 6. Now, in terms of an approximate answer, all of those turn into about 1.839. So you go ahead and you plug it into a calculator and you're feeling good. You got an approximate answer. Okay, now that was actually less work than the first one, but doing the logarithm thing it's a little tricky in the brain. Okay. Third example. Now here we've got a thing going on. Exponential again, but there's extra stuff packaged in here. Right? We've got this plus 8 business, so you're going to want to move the 8 over, so it's 12 after subtracting 8. Then you're going to want to divide by 6, because that 6 isn't helping you out here. Then change into logarithm form. And that's wonderful. But as a reminder, log base e means ln. That's the whole point of natural log. And I rewrote 0.25 as 1/4 because I'm going to multiply both sides by 4. Now, if the 0.25 part hadn't been such a nice looking decimal that turned into a nice fraction, you could have just divided both sides by 0.25. No, nothing special about that. So, in terms of an exact answer, you get 4 times the natural log of 2. Let's see, for an approximate answer, it's about 2.773. Calculator work and you're there. Okay, those are the first 3 examples. The ones that start exponential are there. Now, those are also kind of the easier ones, so let's go again. Now, this is a logarithm equation on example 4, and the nice news here is that it's actually not really a logarithm equation because they're both log base 7, and they're both equal to each other. So 6x minus 16 equals x minus 1, because the thing inside the logarithm has to be equal for the logarithm to be equal. That's actually because logarithms are one-to-one functions, but don't worry about that too much. It's just always true. So you need to move the x, you move the 16, and you're talking about that. You got x equals 3. Now, yes, x is 3. Or is it? So what you got to do, and this is super important for every logarithm equation, didn't actually matter back on exponential equations, but you really have to check. Now, I'm going to show the check here. It will be tedious to watch. I can only assure you that it was tedious for me to draw, and it remains tedious for me to talk about. Of course, you don't need to show the check while you're doing your assignments or whatever, but you'd be goofy not to do it. So, on the left you plug in 3, and so it's log base 7 of 2, and on the right you plug in 3, and it's log base 7 of 2. Well, heck, those are definitely the same. So, yay! And so I will say x equals 3, and I'll box it and sound happy about it and all those good things. Okay. Again, you don't have to show the check, but I need you doing the check. Okay, next example. Here, it's not like a log and log on both sides, like example 4 was. It's a log on one side, and the variable is inside the logarithm. So you're stuck changing it out of logarithm form into exponential form. So 5 to the 2 equals 3x minus 8. Remember, when you change the forms, the logarithms and the bases and everything kind of shifts around a little bit. Let's see, so 5 squared is 25, so you have 3x minus 8. So you add the 8, and you're ending up at 33. So 33 equals 3x. Divide by 3, and x equals 11. And you're like, okay, 11. Maybe. You got to do the check. So we're going to do the check. And, it's a check. It isn't any more exciting than it was in 7th grade when you did it with little linear equations. You put the 11 in for the x, and you're like, hey, maybe it's 2. And so you do it again in log base 5 of 3 times 11, so 33 minus 8 is 25. And then you should notice that log base 5 of 25 is in fact 2. But, if you wanted, you could evaluate that on your calculator. You probably have to change the base. But, hey, it worked. So x is 11 is yes. Good answer. And there's 6 examples, and the last 2 I've talked about checking, and this one's also a logarithm. So this one, the checking must matter. And you're right, but let's get there first. Okay, we got log. Here we've got 2 logs, but they're not equal to each other, and they're added? What? Ooh, there's a property. Yes, those properties that says that if you have 2 logarithms added, it's the same as 1 logarithm where the things are multiplied. Oh, look at that. They're multiplied. Now, I'm going to rewrite this to try to be nice. So this is like 5x squared minus 5x. And, of course, when you see log, that really means log base 10. So there's a little reminder about that. Most of you remembered, and the rest of you were like, oh, yeah, I should have remembered. So that matters because now you know the base. So it's going to be 10 squared equals 5x squared minus 5x. And, well, 10 squared is 100. So it's 5x squared minus 5x. I'll move the 100 over. Minus 100 equals 0. Oh, quadratic? Huh. Well, let's factor out the 5. So it's x squared minus x minus 20. And, you could use the quadratic formula. There's no shame. Your friends might mock you. In calculus, I would probably mock you slightly, but it would work. But it factors nicely and easily. And so you're like, oh, yeah, 5 and negative 4 and other quality numbers such as those. Actually, just those numbers. Maybe not even those numbers. You got to check. Now, this one's a little more annoying because you've got 2 numbers to check. This means you need to check each number separately. So let's do 5, because got to start somewhere. So log of 5 times 5 plus log of 5 minus 1. Maybe that's 2. Yeah, maybe. Well, 5 times 5 is 25. This is, almost insulting. I'm sorry. 5 minus 1 is 4. You certainly knew that. And I would, at this point, once you have it just at number stage, I would just put it in a calculator. There's no point in being extra grand about it. But it does work out, and it's 2, and you're like, yay, 5, yay, 5. But you still have to check negative 4. And so, yes, check negative 4, and you take the negative 4 and you put it in for the x, because that's how you substitute things. But obviously, you know that. So I put negative 4 minus 1. Maybe it's 2, maybe it's not. Let's go see. 5 times negative 4 is negative 20. And negative 4 minus 1 is negative 5. Again, I'm on that thing where I'm saying things you obviously know, but now it's broken. In fact, if you try to put them into your calculator, you're not thinking, you're just doing, which is fine, and at times you do that. You're like, error, and you're like, oh, maybe I hit a button wrong, or hit the wrong minus negative button, and then, no, it still didn't work, and you're like, oh, that's right, I can't do logarithms of negative numbers. Yeah, or rather, no. Okay, so, it didn't work. Okay, so x equals -4 is extraneous. Now, this is a keyword that, it's going to come up. It's going to be like, hey, write down the answer and, draw a target around the extraneous one or something. So it might show up in the examples, the instructions somewhere. Extraneous, it means an answer that isn't really an answer even though you haven't done anything wrong. So I may have mentioned this earlier. I suspect I didn't. Extraneous answers, though, it's different from middle school algebra style problems where you had to check your work, and that was fine, but checking was basically checking against your own errors, and it still can be, but here, though, you have another way of being wrong, even though it's not your fault. It's like you did all the normal symbol work just fine, and I did not make any mistakes on the left that I know of, but no, I didn't, and then you plug them in, and one of them breaks, or maybe both of them break, or who knows what, but if an answer breaks after doing the work correctly, it's not your fault. It's just the funny way that the logarithm properties apply, and they, etc. So sometimes they give you extra answers. Long teacher ramble, meaning check your work. You do not necessarily have to show that you're checking it, but you really got to do it, because you will just end up with wrong answers, even if you're doing everything else perfectly, if you're not checking your work. But that's all I have for you today. So next, we'll have a worksheet in class next time on all sorts of fun equations to solve. Then we'll have a review. Then we'll have a test in a few days. So thank you for watching, and please let me know if you have any questions.